Okay, so well, welcome to How to Design Electronics. This is our third of 7 that I'm running this year. And really, the whole series is really about giving you tips for your own electronics. And everything we look at is all available to download. If you look on the meetup, there is a link, so you go to that, you can just download. So there's no circuit to give away today because it's not really much of a circuit, but you know, we'll look at a little bit of tools that are useful for designing logic circuits, and it's a little bit of maths, nothing brain aching, I promise. And of course, the obligatory experiments. It's always good to do experiments live. As I say, because it's live, remember, anything can happen. Anything can go wrong. Last time the video went down the drain. And one of the comments I did have last time was the feedback I got was, you know, maybe stuff I'm showing, you know, for some people might be a little bit so beyond the introductory, shall we say. But that's really what I want to share with you, is the stuff what I do as an engineer. I've been doing this for 27 years now, electronics. You know, a lot of the introductory stuff, there's a ton of it on the web. You know, there's a ton of stuff on YouTube, and you know, Arduino books, and you know, all the others. So I'm trying to show just a little bit of added value beyond that's what I want to share with you. So my name is Stephen Clemmet, and you know, if there's anything you want me to go over as we tickle along, by all means, give me a shout, stop me. Right, so this one's all about logic, and all computer chips, you know, tend to have like millions and millions of logic gates in them. I happen to have here, if I can share a screen, if this will work. Here we go. Hopefully, this is when the video might go down the drain. Right, so I happen to have here, before we get on to logic, so this happens to be here. This is a wafer from a fabrication. It's actually it's an AT51. It's a 1980 8-bit microcontroller, and I'm not sure how well you can see there, but you know, there's lots of tiny chips on here, and there's probably hundreds of millions of logic gates. So they are kind of all around us. And whilst, you know, logic, think of it like a light switch, just turn it on or turn it off. As I've discovered over the years, nothing seems to behave the way you think it's going to. So, without further ado, I think the place to start is we'll have a look at some logic gates, just to remind ourselves of what's what. So there are 8 in total, and I thought we'd just quickly run through them, so it'll give us a bit of a base of some of the stuff we're going to be playing with. So the simplest gate by far, of course, is just a buffer, where this is the symbol for a buffer. You see, it's just a triangle. An input and an output, and of course 0 represents, say, it's the logic 0 input, which might be 0 volts, and 1 represents a logic high. If you're using AVR or Arduino stuff, you'll probably find that's 5 volts. If you're using ARM core technology, you'll probably find it's 3.3 volts. So this is called a truth table. And I still write these out, although I've been using them for 27 years, I still tend to write them out regularly when I'm doing logic circuits. And then there's an algebraic expression of the output, which is y equals the a, which is the input in this case. So that's pretty straightforward. In fact, you could argue I could do that with a piece of wire. But it does have its uses, which we'll come round to. Its brethren kind is called a NOT gate, where the output is not the input. So the clue is in the title. And again, we have a logic table where the output is clearly not the input. And when something is the inverse, we tend to just put a line above it. So it's a little bit of notation, which we'll probably be looking at quite a bit this evening. So there's two gates. I'm just going to run through these for us. The next one for us that we can play with is what's called an AND gate, where the output is high, logic high, when A and B is logic high. So I've written out the entire truth table. I've got two inputs, and so the combinations of 0 and 1, there's going to be 4 of them. And for an AND gate, we tend to denote it just with a dot between the two. And then we have a NAND gate, which essentially is not an AND gate. Again, I always write out the truth table. And even though I know this from years and years, I still write them out just so I'm clear in my head when I'm designing. And you'll see here, when it's the inverse, you see we just tend to have the same symbol, but there's just a little bobble on the output. And that just tells you it's an inverted output. And where, as we said, with the NOT gate, we had a bar. We just had it over one of them. Because it's now two inputs, we just do a bar over the entire lot. So that's a NAND gate. So the NAND gate is probably one of the most fundamental gates. You can do everything with a NAND gate. Right, there's another two more. Can you believe this? 8 in total. There's an OR gate, where the output is logic high when A or B is high. So again, the clues in the title, so there's nothing sneaky here. And again, I have a truth table. A NOR gate, not an OR gate. It's just exactly the inverse. So you can see there's a whole pattern here that's building. And when we do OR, it's a plus. Whereas, just to remind ourselves, going back for a second, you can see the AND, we had a dot. So these are algebraic expressions. We're going to be using these in just a moment. And the last one here is called an exclusive OR, where it's a little bit like the OR gate, but with the OR gate, I'll just bring that one back for us. There we go. You can see, so it's very similar to the OR gate, except when they're both 1, the output is 0 for exclusive OR, as opposed to 1. Yep. And not too surprisingly, the exclusive NOR is just the inverse of the XOR. And the symbol here is a plus with a circle around it. So there's just a little bit of background on all the gates that you'll ever need to design your electronics, your logic. So what I want to share with you next is something that will help you design electronics. Now you think of this as a little cheeky crib sheet. So if you're designing a logic circuit, I always have this handy within arm's reach. So there are what's called identities. This is just to make your life easy. So I've got here an identity which is an input A, and I happen to have two inputs the same, but if one's 0 and the other, or one's 1 and the other's 0, well, the output can only ever be 1. So this is going to become useful in just a moment, particularly this one. This is called an identity. The next one here is as an AND gate. If you remember the dot, yeah, printed off here for us so we can all see it. So it's almost like having an AND gate where both the inputs are the same, but one's just inverted. And of course, 0 and 1 in an AND gate, or 1 and 0, the output is always 0. So whenever we're creating a logic circuit with all these gates, and if we start to see patterns emerging, we can go, aha, yes. We can start to simplify our electronics. And certainly, if you design like an FPGA, for example, then you might just have NOR gates and NAND gates, and you might want to just try and reduce the amount of logic. We're going to look at that in just a moment. This is fairly simple, this one here. This is just a double inversion. If I've inverted something and I invert it again, I must be back where I started. So these top three are reasonably self-explanatory. These last two here, I'm not going to get into the derivation. You just kind of have to swallow that they're true. But what these enable us to do is to change. This is an AND function. We can change it into an OR function, or in fact, it's actually a NOR function. So we can actually change gates from one gate to another gate and still get exactly the same function out of it. And the reason you might want to do that is if you've designed a circuit, a logic circuit, you might have some spare gates lying around that you'll be able to use. Or, you know, if you're designing an FPGA chip, you might just have OR gates or NAND gates available. So being able to think, all right, I've got an AND function here, but my FPGA is only, let's say, NOR gates. Well, actually, I can actually do an equivalent circuit to get what I want. So you're not tied to using all these 8 gates. You can actually mix and match them a little bit. And this is one identity, just to turn an AND function into an OR function. And you can turn an OR function into an AND function. So these are a little cheat sheet, shall we say, that just print it off and just have it to the side. And we'll have a little play with this in just a second. So there's a couple of things so far. So all 8 gates and some logic identities or a cheat sheet. So we're going to come back to this in just a second. So how about an example? So I've made here a little example for us. So whenever I'm designing a circuit, it's the sort of thing I still do this today after 20 odd years. Let's say I've got, this is just my example. I've got a black box, I've got 3 inputs, and I've got 1 output. And I always draw a truth table to make sure I cover every single eventuality. So if I've got 3 inputs, I must have 8 combinations of light switches being on and off. And so just in this example, I've just done these in red just so we can see them a little bit easier. So just in this example, I've just decided with A, B, and C that if A is, say, a light switch saying off, logic 0, and B is on and C is off, my output is going to be high. And I've done some others here. So draw a truth table first, and then using these logic expressions we've just seen, we'll then create an algebraic expression for what's going to go inside of here to design this circuit. And it goes something like this. So I'll say y equals. Now I've got, in this example, I've got 4 things I want to be happening. So I'll do, right, I've got, I hope you can see that. I've got not A and B and not C. Okay, if I get that combination, then my output will be high. Or, which is a plus, I got that being high, A high, B is low, and C is high. That's another combination. So if I get that or that, the output will be high. And I do this even today after 20 odd years. Or I've got A is high, B is high, here, and C is low. Yep. And the last one, quite straightforward. So we can see there that to design this logic circuit from my truth table, and I always start with my truth table, which is what we call it, because it's the truth, I can get an expression which tells me what will happen to my output depending on what my inputs are. And then all I need to do is just draw it. And in the interest of time, here's the answer. So in this example here, I've just got the same thing written out here so we can see it. So if I am drawing a circuit, logic circuit, and I might just my A, B, and my C, I'll draw a line, and I might just start with just draw a NOT gate. So yeah, that's my A NOT, that's my B NOT, and that's my C NOT. And then essentially I've just got a 3-input AND gate. That's fine. You can usually buy up to 4-input NAND AND gates if you want to. They exist. So I've clearly got 4 of these. Got 1, 2, 3, 4, and here they all are. And then I'm going to OR them together. So I've now got an OR gate, and that will work every time. There's no problems with that at all. But what I'll show you in a sec is, can I make that simpler? Whilst that would work, and I probably have quite a lot of wires sticking out of my breadboard, can I make that easier? And the answer, of course, is yes. So I'm going to show you, we'll come back to this in a second, we'll compare this with something that is easier still to do. And so we'll look at that in just a second. So can I make that easier? Well, here's the answer. It's called a Carno Map. And it was invented by a chap called Maurice Carno in, I think it was 1953 from my research. And it's a way to simplify what's going on. So I start again with my original, just covering it up there for good reason. I carry on with my original truth table, which I had before, and I'm going to transpose it into this strange looking table, which is called the Carno Map. And then I'm going to create a logic expression for this. And what we will find is that it should come out a little bit easier. So this is how it works. I'm guaranteed this will work every time, but there are some rules you've got to follow. So I've got 8 combinations here, and I've got 8 possible combinations here. And all I've done is transpose. So I've got A and B here together. You see, and I've got 0, 0, which is A and B 0, and C is 0. Yep, and then I've got 0 and 1, which is that one, and 0, C is 0. And then I've got 1 and 1, and 0 is 1. As you can see, it just carries on. Now what you'll see is, of course, I've got a slightly different ordering of my numbers here in my columns, and that's really important. Because if you look very carefully at this Carno map, what you'll see is that any adjacent square only has one variable that will change. For example, between this one and this one, C doesn't change and B doesn't change, only A changes. And we could pick this one and this one and this one. A and B don't change between these two, and C does. And that's the trick to the Carno map. So what we're going to try and do is create a logic expression for this table, which has come from our original truth table. Now, going back to the identities, this is when you have your identities to hand. This is when you want to have your identities next to you, because we're going to use this top one, which is the most useful one for doing this. So I'm going to use this identity here. So it's just worth having to hand. And then what you have to do with the Carno map, you start pairing things up. So if there are adjacent numbers, we just draw a circle around them. So you draw circles in things that are in 2s or 4s, or if we had more down here, you know, if we had a D in 2s, 4s, and 8s. You can't pair things in 3s, and you can't pair things diagonally. So I've clearly got a pair there. These are the rules, and I've clearly got a pair there. Yep. And then all I have to do is create an expression for these pairs, and they're going to be all together. So let's do that. So our output Y, here it is. We've got B stays the same, doesn't it? And we've got not C. I haven't written down A because A changes. So it doesn't matter if A is 0 or 1. It's irrelevant to this expression. Or the other grouping, which in this case is going to be A, because B, we don't care what it is. It's irrelevant for this pair. So we've got A, and we've just got C. So if we draw that out, it'll look something like that. And I think you will definitely agree that that has got to be easier to make than that. You know, that might be a challenge. And I'll also add that the chances of making a mistake in this rather complicated one is significantly higher than this one here. And you can see, look, my gates, I've got less gates. I've only got 2 input gates here. Here I've even got a 4 input here. So this is going to be more expensive. It's going to be bigger, and it's going to be a lot more wires. It's not going to be pretty. So what I wanted to do, just to prove to you that I'm not making this up, I thought what we'll do, we'll just enter this into our Z column and compare it to our original output for Y. So let's give it a go, shall we? So follow along. B and not C. So here's B, and here is not C. Yep, good stuff. Is there anywhere else? I don't care what A is. Oh, it's here as well. B and not C. Okay, that looks good. Let's try this one. A and C. Right, where is A and C? It's that one and that one. Yeah, so that's good. And the only other place I can see where A and C, it's that one. So there we go. And clearly they're 0. So there's the proof that that circuit is exactly the same as that circuit, and yet I've used less gates and less of a problem. Good. Right, I hope you're all still with me. Right, I think it's time to do an experiment. So this is where things can definitely go wrong. I haven't heard anything from anybody, so I'm assuming the video's still working for you all. Right.
Yeah.
I always try and make a little circuit for us, or something to do on a screen. So it's a great time and enjoyment. I've designed a small logic circuit. So we're going to have a look at another type of gate. Gosh, yes, there is one more. I didn't mention it, called a Schmidt Trigger. It was probably invented by Mr. Schmidt, I suspect. What it is, it's a gate, and we're going to look at this on the oscilloscope. There are our normal gate, which I've got here, and then there's something called a Schmidt Trigger. If you're not aware of this, It functions exactly the same as your ordinary gate, but it has this funny little sort of squarey hypotheses, hyperbolic, offset. I can't remember what it's called. It's got a magic term, which I should have looked it up.
So hysteresis?
That's the word. Yeah, thank you. So with a normal gate, you'll have your input, and we're going to look at this on the oscilloscope. So your input might slowly change, and then there's a threshold level at which it will decide it's no longer going to be a logic 0. That's logic 0 direction, and that's logic 1 direction. So in normal gates, there'll be a thin line in the sand where you just want to get through, you call it the grey region. You just want to get through that as quick as you can. And hopefully we can see on the oscilloscope what happens if you don't. There's then something called a Schmidt Trigger, where it has 2 threshold levels. So if you are dithering, let's say you're dithering, I'm a bit of a ditherer, let's say, something like that. When it gets past the first one and it triggers, it doesn't matter if it dips below it again to start with, it won't then cause a problem with the output. Well, here if we dithered, you know, we might not know if we're coming or going if we're in this little area around here. With a Schmidt trigger, they give us 2 trigger levels, one here and one here. So it won't trigger the other way until it gets to the next one. And one of the things I discovered, I've always discovered something right in these sessions for us. I was always thought that these Schmidt triggers only ever existed in NOT gates. You only ever see them in NOT gates. But I discovered in writing this and doing some testing that this Schmidt trigger actually does exist in some other logic gates, like AND gates and NOR gates. Because while I was trying to test it, I just couldn't understand why I wasn't seeing this dithering in an ordinary gate. And it was because they now put it into standard gates as well, which doesn't seem unreasonable to me. There's no mention of it in the datasheet, but it was evident on the screen. Right, so what I'm going to do is I'm going to swap to a different camera, to what I call desk cam, if I can. Oh, that's interesting. Oh, there we go, there we go. I've got it. Right, it's going to swap. Yes, there it is. Right, so I've got what I call desk cam. Right. So what I've got here, I've got a. All right, let me just show you here. Let me just jump back here so you can see in your mind's eye what we're going to be looking at very quickly. Right, so oh, there we go. That's lovely. Right, a bit of a zoom job. Refocus. Right, so what I've created here for this is just a power input here, a bit of power circuitry. I've got a signal generator coming in here, and I've got an ordinary gate, which we'll have a look at and see if we can see this dithering. And then I've got a Schmidt trigger version here, and then we can just look at the outputs of those different gates. So I will now swap to camera 2. So fingers crossed this works. There we go. Right, so if I actually change to, so the yellow line is my input and it's a square wave. And my blue line is actually the output of my logic gate. So in this example here, I've initially wired it up for the ordinary gate. And on the face of it, it does look like everything is sweet, doesn't it? It looks like I've got a sawtooth coming in. This is my sawtooth coming in. And it looks like everything's great, you know, and it seems to have the same transition point here and here. This is sort of roughly in the middle here. So that's looking good. But what happens if we slow this saw wave down, so we start to dither in this region. Let's fingers crossed it worked earlier. So I'm just going to change to a much slower speed. And everything's looking great at the moment. And fingers crossed, we might start to see this is when it may or may not work. It wasn't that easy to get it to trigger earlier. Oh, this is when live events don't quite go to plan. Right, so that's clearly not. Oh, there you go. Did you? I'm not sure if you saw that then. Sometimes what you'll see is you'll see like another pulse. So because if it's dithering, of course it's now behaving. Now we're live. But earlier, of course, it didn't play at all. Oh, if we could just capture it. Oh. In fact, it is doing it because you can see sometimes that the oscilloscope is sometimes, although I'm triggering off the output, sometimes it went up and down. Let's see if I can capture it when it does it. Oh, it's always the way when you want it to not play. Give it a sec. Let's see if we can. Okay, so it's not playing. Okay. Always the way when you want to. Come on. Right, you see it flickering about there, and then it's normal. So what it's actually doing, and I'm not being, I can't seem to capture it, so I'll draw it for you. Plan B. What it's actually doing is the. Stop there. Oh, hang on, that's right. 1 moment. There we go. Now you can see it. What it's actually doing is, when it'll do it, is you think it's going up and down like that. But what's really happening, if you're dithering in this no man's zone, and you zoom in to this edge here, you'll see it's actually doing lots of this sort of nonsense. You'll see it's actually just got a lot of random switching, and that's because you're dithering. And I can't seem to make it want to capture it for us, which is always the way. However, let's not worry about that. Let's go back. Right, okay, let's not worry. Let's move on. Let's just swap back to camera 2. Right, so okay, so that's not playing for me today. However, it matters not. There we go. That'll do. Right, just trying to get rid of that. There we go. I just stopped the oscilloscope there, trying to capture a full trace. So you can see here, if I do cursor on, get rid of, oh, get rid of that one. Right, let's use this one here. So I've just moved the cursor line down to the trigger point. So this is the trigger point here for logic low. And this is the trigger point here for logic high. And you can see it's pretty much exactly the same. Now let's compare that with a Schmidt trigger. So with a Schmidt trigger, you can actually see, we'll bring in the other one here now. You can see here, what we're saying is, there we go. So look, so we've actually got, we're saying, 2 definite threshold levels. So if I'm using, say, an analog circuit, if I was using, say, a variable resistor, or maybe I had a like an audio input, I'd probably think about using maybe a Schmidt trigger, because it'll just make sure that whilst I couldn't make it capture it, there's actually no danger of ever having messed up logic levels. And that's one of the reasons why when you're drawing your circuit in your truth table, you want to make sure you capture every eventuality, not just the ones that you think, oh, I want it to do that output when I've got this input. Make sure you capture absolutely everything. Right, I've been talking for a good half an hour. I do have a little bonus material for you. Has anyone got any questions? All quiet? Can you all hear me?
Presumably you only need the Schmidt trigger on the outside of a group of logic circuits, and that once you're into pure digital stuff, then you can use plain gates again.
Yeah, very true. Yes. Yeah, absolutely. Yes, I tend to, if I'm using, say, switch debouncing circuit. So well, we can draw that. We can draw a quick switch debounce. Just swap to let's draw on the back of here, shall we? So yes, so if I was say I was doing some switch debouncing, that's a resistor, and I've got a switch there, that's 0 volts, that might be 5 volts. I might have a capacitor there just to help. Yeah, so hysteresis, that was the word. Yeah, so I might very well just have it on the input. Yeah, and then when I get to my other circuitry, whatever it may be, and whatever other inputs I've got, yeah, I'll just start using standard logic. Absolutely.
There are sometimes when actually having a Schmidt is useful in logic. I think at one point when I was working on a Centronics connected printer, and because the decoupling network was wrong at the other end, basically the strobe line was ringing like a bell and flying way past TTL trigger positive when it should have been driven. Driving low, swinging way into negative, swinging way back up past TTL positive trigger, and settling out over quite a long period. And it's one of those things where, yeah, might be quite a good idea to have a Schmidt in there.
So I'm glad you mentioned ringing. I had it as a bit of a bonus for us. I can actually show you ringing for those who don't know what ringing is. This may this may work. I think I need to just put that on there. All right, just seeing if things are correctly hooked up on my scope before I. Okay, that's not quite what I had in mind. Hang on, just seeing if I can get ringing up here for us. Oh, that's interesting. So I'm just trying. So I did have ringing as a bit of a freebie extra for us. Oh, okay. That's all very interesting. Can I see it on here? So I'm just seeing if I can get ringing for those who haven't seen it. Yeah, we've got it on here. Let me just swap so somebody can see what ringing is. So yeah, so here is ringing. So this is not too bad in my circuit here. So you can see. Oh, get rid of that. How do we get rid of that? Oh, there we go. So here we've got a little bit of ringing in our circuit here. So if we zoom in, let me move it. So there we go. So here's ring. I'll be honest, ringing is usually down to layout issues and probably not sufficient decoupling on your board. Because when I first built this circuit, and I was doing some testing on a bit of strip board, yeah, I had some pretty bad ringing. So you can fix ringing. Quite timely you mentioned it actually, so I have it here as a little extra on how you fix ringing. So the way I fix ringing, which I could pop it on here so you could actually see it fixed. Oops, for some reason. Oh right, that's why. Got it. Right, okay, right. So there is some pretty bad ringing, yeah? Where this here is called overshoot. So this is our main signal here. So you see we've got a bit of overshoot, it's just what's being described just then, and then this is called ringing. Now it's quite easy to fix. A lot of it comes down to the layout. So in logic circuits, it's quite undesirable. It can cause problems with radio emissions and EMC. But I'll just show you how one way to fix it, an easy way to fix it. That's a lot better, would you not say already? And I'll show you the circuit of that in a second. And then here it is completely fixed. And the way which you can fix that, this is a little top tip. This was a bonus extra. I wasn't sure if I was going to have time to share this with you, so I'm glad you brought it up. So this is how I fixed it. So, disappear. Here we go. So here's a circuit that will fix ringing. So my ringing here was originally on X. So I just had a square wave running in here. And as you saw there, I saw that ringing. It looks like that. So you'll see it when you zoom in. So you can fix it just by loading the output. So 50 ohms I've just impedance matched, and this is and I actually found this by experimenting. I calculated it should be about 50 pico. It turned out 100 did the job. So I was measuring on this line Y, and it was looking better, and on Z a second ago it looked better still. So it's quite easy to fix. Yeah, I mean you fixed it with an inverter, a Schmidt Trigger rather.
I wish we could have fixed it with a Schmidt Trigger. I ended up fixing it in software because we weren't able to do anything with the hardware. Basically, by making, yeah, I fixed it by making the strobe pulse so short that it really didn't get enough energy to overshoot.
Right.
But that would I mean it was the only tool left in the box at that point. we were down to the printer manufacturers and the sort of decoupling network that they had, and it was about a power of 10 off.
Wow, so it was really bad.
Oh yeah, I think we had something like 2 to 3 retriggers every pulse under normal conditions.
Wow, that's very. I've never seen anything like that. I mean, logic does sound, well, it's on or off. I mean, I know when I did my degree, you know, everyone opts to go and do the logic circuits, you know, the logic design, because they think that will be easy. And yeah, the honest truth is, yeah, in the real world, nothing really behaves, does it? No.
I've generally assumed, but I don't know if it's actually going to be true, that you make digital circuits to go as fast as possible. And in fact, it won't really be like a square wave because as soon as it passes the logic 1 threshold, the clock will be on the way back down again. Is that actually true, or do you design circuits such that the 1 is actually a stable top?
It doesn't, yeah. As you start getting faster and faster, you start getting into RF territory where things really don't behave themselves. No, and I'm not usually waiting for, you know, for it to be, you know, just completely stable. I mean, when we spoke about timers the other week, the big thing to be wary of is that, you know, things don't happen straight away in logic. In fact, one of the things which, again, more bonus material, an extra bonus one. So I took this out because I just had too much material, but I thought I'll keep it to hand in case somebody asks something, and here we are. So binary versus grey code. So what can happen is, because nothing happens in really as instantaneously, in binary, when we go from say 3 to 4, we've got all our bits all changing. So because nothing happens instantaneously, you know, actually when it goes to 3 to 4, on the way from 3 to 4, it could actually be any number at all, couldn't it, really? And so the way which often you'll fix that is, okay, whilst your logic's going fast, obviously, you know, you then have to synchronize it with a clock, and that would have to be a time later to allow the signal, no, the voltage levels of the gates to settle. It's called settle time. So that the clue's in the title, really. Whereas if you went with grey code, if you look at grey code, which is actually what we're using in our Carno map, in grey code, only 1 bit can ever change at a time. So from 3 to 4 in grey code, well, I've only actually got this bit here changing, so I can't ever get lost. Which is why, you know, when we're doing the Carno map, if you remember our Carno map from earlier, this is actually grey code in here. So you can actually, if you look up grey code, it'll start to make a little bit more sense as to why we're doing it that way. But yeah, I mean, you have to wait for things to settle, for sure. But it doesn't need to be right at that voltage level. It depends on the circuit, of course, and what you're trying to achieve. The other thing we're trying to go super fast is the faster you try and go, the more power you're going to draw, and the more radio emissions you're going to generate. So, you know, do you need to go that fast is the question.
Yeah, I mean, the philosophy from where I've been sitting has always been designed for exactly as fast as you need and no faster, because ye gods, EMC compliance is a pain.
Oh my gosh, it's a dark art. Well, we're going to talk about that. I think it's the penultimate. I think it's 3 months' time. We'll talk about, you know, that black art. It's a fascinating subject. It's the one that nobody thinks about until after they've designed their product. And then somebody says, so what about approvals? And yeah, and then the wheels come off the cart.
Oh, by the way, you did isolate the analog and digital sides of the circuit, didn't didn't you?
Yeah.
Oops.
I've seen so many times. When you go for EMC, the electromagnetic compliance, which is a legislative requirement, the horror stories that they will tell you about things that haven't gone right. I'm not sure. Did I tell you the one the other week about Pinewood Studios and the boat chase scene, that blew up? Okay, this happened about, it must be more over 10 years ago, 10 to 15 years ago. This happened at Pinewood Studio, where they're doing a boat chase scene, so your mind races to Bond. I don't know if it was, but suddenly all the pyrotechnics blew up on site. And when they tested it at EMC, they found the equipment was susceptible to radio waves of a certain frequency. And so back at Pinewood Studio, they did an investigation, and half an hour before the pyrotechnics blew up, somebody had ordered a taxi. And the rest you can work out what happened when the taxi arrived with his slightly illegal ham radio. Yes, I'm here. Off went the explosion. So yeah, EMC is a nightmare. And if you've got clocks going, or if you've got lots of logic edges going and they're going all the time, like they might in a memory system, for example, you can expect trouble, particularly if they're going all the time. On the subject of trying to solve this ringing, product I've been working on recently, a medical product, we've had a devil off a job with Maxim, who are meant to be a very respectable company. They actually capacitively loaded their data ports to try and reduce EMC. But it was on an I2C port, which is a communication bus, which we'll probably get to talk about. We'll probably get to talk about that in Series 2, when we talk about I2C and SPI.
I can see where this is going.
Well, the capacitive loading, which they put on their I2C line, meant that when we started adding other I2C devices, the capacitive loading actually completely destroyed the integrity of the I2C signal. That had us going in a merry circle for quite a while, trying to work out what it was. In the end, we had to put the chip on its own I2C port because they'd capacitively loaded it to the point of trying to reduce. In fact, we go back to here. Where are we? Yeah. So they had in their circuits. Where's it gone now? Yeah. So they had such a high value here that it caused the output really to start to slope. And of course, if it's too large, you might end up being below the threshold level before you want to go logic 0. So you can overcook it.
And then everyone, of course, does their own decoupling, and you've got a very gentle little sine wave going on. Yes.
Well, that's one way to create a cheeky sine wave, isn't it? It's just to put an RC circuit in. And I think we've all done that, in our early days of electronics, to try and create sort of dirty looking sine waves, and then try and put it through a speaker, and it usually sounds pretty awful.
Do you recall what level of capacitive loading was on the outputs?
Of the chip we just had?
Yeah, the I2C chip.
I don't know is the honest answer. I can't remember. I think I did calculate it, and it was surprisingly high. Because don't forget, the I2C was going at 100 kilohertz.
So the resistor level that you were using as pull-ups was driven how low?
Oh, right. I think we ended up driving that. Well, we started off doing exactly that, of creating a smaller and smaller pull-up resistor, and it's we've got down to, it must have been less than a kilo ohm, which is
okay.
You definitely should not be doing that.
No. That's quite. I mean, was it long tracks involved as well? Presumably not.
No. no. I mean, my circuits these days are really tight. You know, the track length, you know, couldn't have been more than, you know, sort of 20 millimeters.
Oh,
It was a nightmare trying to crack a problem. And this is what happens with third-party devices. I'm getting on my hobby horse now. Third-party devices, if you haven't used it before, and even if it seems really simple, treat it with an air of caution. You know, that was the moral of the story. Yeah, so we ended up, the way we fixed it in the end was we had to put the chip on its own I2C port. Now, fortunately, because we're using the ARM Cortex M4, it had a number of I2C ports.
So completely destroying the notion of it being a bus. You sort of isolated it and put it on the step.
Absolutely, I had no choice. Yeah, to make this thing work. Yeah. I'm sorry to say, Maxim have a very good reputation. You know, engineers love their chips to death. And a cat trying to annoy me. Go away. Demanding attention. I get that all day working at home.
Well, now you've got an electrostatic noise generator. You can demonstrate the Schmidt trigger.
Oh God, yeah. There's a pair of slippers in that, I tell you. We solved the I2C. Yeah, completely destroyed the notion of an I2C port. But so these things happen. So as I say, you know, with electronics, all electronics, nothing behaves exactly as you think it should do.
Thinking of I2C, SPI, and so on, and also power circuits that were mentioned in an earlier session, are they likely to interfere? Because one of the projects I've got in mind is to trickle charge my camper van controlled by a Raspberry Pi, which is in the garage anyway. So you can get I've just drawn up the data sheet here, 3008 ADC uses SPI, and there's also some I2C ones available. So have something which will monitor the battery voltage via the Pi, which can then operate solid state relays to switch a 15-volt power supply on to top it up for a while. And it'll also serve as a theft alarm. So if the voltage disappears completely, I know somebody's disconnected it. But in that sort of environment where I'm switching power supplies on and off and routing the power supply output to different batteries, all on the same Raspberry Pi, are these likely to interfere and make the SPI glitch and things like that?
Well, there's a number of things. The answer is, I believe, yes. Okay. I think you're going to have more problems than you can shake a stick at. Yes, exactly what will happen. So some of the ways you can deal with that particular issue. Let's see now. Well, I2C is really a board level interface. We're getting about 6 months ahead of ourselves here. But I2C, of course, is a board level interface. It's not designed for going off board, really. If you want to go off board with I2C, then you really need to go via a differential driver. However, we have had issues with this happened on the ARM Cortex M range. We actually did have a differential I2C to go off board, and we actually managed to make the ARM core hang under EMC conditions. And yeah, it took some clever filtering and some very clever PCB design. We'll talk about PCB design. I think it's July. It's the last one before we have a summer break. But yeah, the PCB layout will be absolutely everything. Yeah, if you're turning things on and off, yeah, you can definitely expect to have power glitches. You know, when things like you've got capacitors on board, well, you know, they're gonna want to charge up. So yeah, you're probably going to be in for a rocky ride, believe it or not.
Yes, at least everything will happen very slowly at the application level. You know, I could afford to not take any samples for a second or 10 seconds after.
That's exactly how you do it.
Sorry?
That's exactly how you do it. Yeah, you just again, that settle time, allow for that settle time until, and so it can breathe again, and then you're back in the game.
Yes, I mean, it only needs to take a sample every minute. Even every 10 minutes would be enough.
Oh, okay, fine. Yeah, just don't try and do things on that transition, because yeah, the logic will get dangerously upset with you.
Okay, yeah. And when you were saying it's an onboard type of connection, would using it on a Raspberry Pi hat, the board which actually fits on top of the Pi?
Oh, that's fine. Yeah, you're going there for a short connector. It's just you don't want to run I2C or SPI. Those interfaces, they're not designed for running over long cables.
No, okay.
Is what I was saying.
Right, but within an enclosure or on a
probably in an enclosure probably be fine. But don't forget as well, cables are the undoing of every product. When it comes to emissions and reliability, which is our penultimate one this side of the summer. When we talk about reliability, the things that you're describing, we'll have a bit of a deep dive into how can we solve those problems. I mean, opto couplings is an option.
Mm-hmm.
If things are going to be a long way away, and if you've got your Raspberry Pi, and then you've got some sensor, you could run, maybe RS485, which is, pretty industry standard, rock solid. It's just a differential UART, which is dead easy then to set up. That would probably be the way I would do it.
Yes, in this case, it's just a battery voltage that I'm sensing directly, so I don't need any input transducer. It is already a voltage.
Oh, okay. So yeah, the things you want to put on the line are probably just suppression devices, ESD suppression. In fact, if you just bear, I might be able to just find one here and then share with you. Just bear with me a second.
Oh, yes, because the line is going to be about 10 meters long, running from the garage to the vehicle.
Yeah, you're gonna have you're gonna have a problem.
Be hit by lightning.
You are going. Yeah. You're definitely. Yeah, you can't run ITC over that.
Oh no, but this would be from the vehicle to the box which contains the Pi, the power supply, the ADC, and everything else.
Yeah.
And
John,
it's a long wire, I presume, because of the very high impedance of the ADC, that the voltage drop won't matter along the wire because there's basically no current. So all the logic will be in one box in the garage. The only thing at the other end of the vehicle is, at the other end of the wire, is the vehicle's lead acid battery.
John, can you hear me?
Yes?
John, I've been playing around with the Raspberry Pi and the Arduino, and I use a company called seedstudio.com.
Oh, I've heard of that, yes.
And they have an absolute amazing set of sensors that are full wire sensors, power and signal, and you can drive them quite a long way.
Yes. Yes, but in this case, all that it needs to do is monitor the battery voltage. Say, if it goes under a certain level, turn the power supply on for a few minutes. If it drops down to 0, tell me.
Yeah, you can get those. You can get voltage dividers and all sorts of little remote sensors that you can bring into the Pi. It's relatively easy to do. I've done it, and I'm not an expert.
I'm going to share a new screen with you here. I think this is the one I want. Right, hopefully that's sharing with you there.
Yes.
So I actually, when we're talking about logic inputs, and if you're running over cable, I put these tiny surge arrestors. You can get these from, all good electronic suppliers. So I'll usually just put one of these between, the input pin and the ground. And, so if you do get any transients over cables,
okay, yes.
then, you'll protect the circuit. And now I put the circuit, and I've had circuits under ESD tested to, I think, plus minus 8,000 volts, which is basically, if you wear your favorite nylon shirt and and then touch the circuit. These devices will save your electronics from being fried.
Okay, that's a good point. Yes.
Because what you'll find is, certainly with logic circuits, they work great, and you walk across the carpet, you build up 10,000 volts on your shoes, and then you touch your board, and it'll carry on working absolutely fine. And then 6 months later, it'll just keel over, and you'll have no idea why. And basically, you've got away with murder. So yeah, so it's another little golden nugget. So I've been putting these on my logic circuits. If I've got like the Raspberry Pi board, for example, or your hat, on the inputs, I always put these ESD protectors to make sure the circuit doesn't fry. And I've done quite a lot of EMC testing with these devices, and they've never failed me.
John?
Yes.
I was thinking about something similar to what you were just saying as well, because my motorhome has obviously got a leisure battery and a main engine battery.
Yes, likewise with mine.
And what I was thinking of doing was using the voltage sensors. And then what I've done in the past, I've just got the Raspberry Pi to drive an app called Blink. And Blink is incredibly easy to use. So you could quite easily monitor your leisure battery and your engine battery on the Blink, on the Blink app. That works. It's not that difficult either.
Yes, well, I can probably write, it'll be a very small program I'd need to write anyway.
Yeah, it would be for the Raspberry Pi. Yeah.
Yes. Yeah, it's not got to be fast. It's got to respond in minutes rather than microseconds.
Yeah.
Oh, that's an eternity.
Yes. Yeah, I can do it in an interpreted language like Python.
Yeah.
Yeah, that's what I've been using, and far better, John, than suddenly going out to your van one day and finding that your battery's had it.
Exactly, because with lockdown, it's parked there a lot more of the time than it was
Yeah,
before.
I know exactly what you mean.
Good stuff. Has anyone else got anything they want to chuck into the melting pot?
Yes, so Stephen, I'm guessing that all these logic gates are typically built on silicon semiconductors. I mean, presumably you can get valves, but who would do that?
Yeah.
Are there any sort of variants? Do they come in different specs? Do they switch at different speeds and things like that?
Oh, yes. Very, 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 very good, deep question there. Absolutely. It's one thing I didn't really touch upon. Yes, they do come in different flavors. When I started doing this back in the early 80s when I was a kid, of course, nothing worked and Dad had to fix it. I started off with CMOS technology, where things are as near perfect, of half the supply rowlet triggers. Of course, the other old school course was TTL logic. And you shouldn't really be mixing your TTL and your CMOS because they do have different switching levels. And you could end up in that race hazard issue where things change and you get a spurious data result coming out of it. So yeah, there are different technologies. CMOS and TTL are the two most common ones. I would say in the last sort of 10 years that I've been designing logic stuff, they're usually, when you look at the code, 7.4 usually means it's going to be a TTL type device. But now they blur the line a little bit because they'll be, between after 7.4, which means it's a TTL, it's usually just TTL logic level. There'll then be a collection of letters which will be about, well, is it like low power? Are they Schottky diodes? Are they is it actually a CMOS circuit with TTL logic levels in it? So it does start to get a little bit blurry. You know, it's a bit like trying to choose a light bulb. You know, you go to the shop and you'll probably come back with the wrong one. But on the whole, you know, in recent years, when I've been designing circuits, I tend now to use more single gates rather, because you can get chips with multiple gates in. I tend not to use them so much now. Most of my logic stuff is actually more the gate I want. You know, like those 8 we had to start with. And yeah, I'm usually making sure that they're usually all the same sort of family of technology types. So I would say just don't mix the technology types if you can help it. In all honesty, I reckon it would still work. I think you know, fundamentally it'll still work just fine. I think it's just more the input. You know, you've probably got to be more careful with what am I chucking into it rather than what's happening, you know, into logic, if you like.
Okay. So they sort of switch at the same speed, and as long as you're not getting up into sort of megahertz rates, then you're probably going to be okay.
Oh yeah, you can get some super fast devices for sure, but don't forget, if they're going super fast, you're going to have ringing.
Yeah,
you know,
and EMF problems and
yeah, EMI, yeah, absolutely. So, but
and also things like skew effects, and you know, you have tracks even moderately long, and you're going to be in a world of fun.
Yeah, if you look at like DRAM, you know, if you're doing fast memory DRAM designs, you know, the track length becomes quite critical.
Yeah.
But for stuff you're designing, you know, with your Arduino and your Raspberry Pi and your ARM cores, stuff I'm doing, I've looked into it. You know, I've done track balancing, track length balancing, and occasionally I've forgotten about it, and it's not made a scrap of difference. So, you know, if you're going super high speed, and I can't see why you would be, unless you're going to start getting into memory management, you know, for your little logic circuits, yeah, I wouldn't worry about it.
okay, sounds good.
It's nice not to have a problem, isn't it? Right, well, look, it's 9:15, ladies and gentlemen. So what I've shared with you, and we've had a chat around, are really the common concepts that I still use today, you know, as an engineer with, you know, I always draw out my truth table, and, you know, I've always using my Carno maps and my identities. So, you know, they're the most common tools that I use that I wanted to share with you today. The next one, which is Wednesday the 3rd of March, I haven't decided exactly what I'm going to do yet. If anyone's got anything they would like me to look at in particular, I'll take it on board. But the next one I was looking at doing was op amps, which is analog. So if anybody, I'm starting to throw this out a bit now, if anybody has anything in particular they would like me to cover in op amps, then you know, let me know now, or you know, leave a note on the cam on the Makespace page, and I'll look into it. And similarly, the one after that, which is in April, I don't know what date it is in April, so I'm going to have a look at that, will be, oh, come calendar. The April one is going to be on, looks like it's the 7th of April. It's going to be on sensors. So if there's any particular sensor you're interested in, I will happily take a look into it for you. And as long as it's not completely, you know, off-piste, I will take that on board and do something. So there we go. So yeah, so you know, it's there to give you some tips and tricks rather than me just talking about me and my favorite subject, which turns out to be me. that's all I've got for you today. Nearly 9 o'clock. Good. Okay. Should we close there?
Thank you very much.
My pleasure. And
Great, thanks.
yeah, so drop me a note if there's anything particular you'd like covered, and I will endeavour to make it happen for you.
Thank you.
That's probably a dangerous thing
thank
to
you,
say.
Lovely.
Okay.
Thank you.
Okay. Okay then.
Bye.
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 Cheers.
Bye for now.